So today I will be discussing formal verification, and so overall first let us understand what is meant by verification, then we will try to understand what is meant by formal verification. So basically the major steps of verifications are like first we need to determine what we need to verify. So that is specifying the correctness requirements for verification, and then we need to model the system, and after that we run verification algorithms to check the specification is correct on that model. Now let us take an example of a vending machine. So suppose that vending machine, we have two options for that vending machine. One is we can insert 2 rupee coin, and another is we can insert 5 rupees coin, and depending on the denomination of the coin, if we insert a coin of 2 rupee, it will give us a toffee, and if we insert a 5 rupee coin, it will give us a chocolate. Now for this vending machine, so we have two inputs, like one is the choice for toffee, one is the choice for chocolate. Now when we press the button toffee, it expects the user to insert a 2 rupee coin. Now what could be the specification of this system? That is, if the button for toffee is pressed, T, and then inserted coin has the denomination 2, then it will output a toffee. So that's how we formally specify the requirements, the characteristic requirements for a machine. Now how do we model the system? Physically the vending machine can appear like a system. So system like this, but to verify this property we need to get an abstract model of this system, because on this entire big machine we need to specify on what component we need to verify and what we need to verify. So what we have specified is we need to verify this property. Now for the model of system, suppose initially it is basically waiting for the user to press a button. Now when a button is pressed, it may be the button for toffee, it may be the button for chocolate. Now whenever toffee is pressed, it waits for a coin equals to 2. So when it's given, it outputs a toffee and then returns to the initial state. If anything else is inserted, it will straightaway go back to its initial state. Now you can add another criteria like some timeout. After pressing the button, the system will wait for say 5 seconds, then it will return to initial state. So that's how abstractly the modeling is done. So modeling means we abstractly create some form of transition diagram, state transition diagram of the system. And the third part is verifying properties over the model. Now suppose this is the property we want to verify. So how do we verify it? If you look carefully to the model of the system, I haven't completed the entire model. Okay, C equals to 5, it gives chocolate. Now from the starting state, it can go to that chocolate state or toffee state or chocolate state. I mean, after pressing the button, depending on the button pressed, it can go to this state or this state. Then depending on the coins inserted, it can go to this state or this state. So basically, if you enumerate the runs of the machine, that means you unfold the state machine, you will get something like this. Some starting from the starting state, you will get a tree form of structure which specifies the sequence of actions, all possible sequence of actions. Now, what we mean by verifying properties over this, we try to verify the properties over these runs. Now, suppose the user wants a toffee, so he presses the toffee button, he comes here, then he inserts a 2 rupee coin, it comes here. Now, what we do is we try to make sure that this property is holding over this run, this run, this run, and this run, these kind of things. Now, these runs can be user can write test cases to enumerate each of the runs, or we can try to exhaustively enumerate all runs and try to verify the properties over that. Now, for chips, this is the basic overview how the chips are manufactured. So first we start with some specification. Those are basically English level English documents specifying what is intended from the chip, and it specifies the high level behavior of the chip, and then the designers makes the implementation. So it may be using Verilog, VHDL, whatever. It creates implementation through some language. Now, this implementation, then from this implementation, the first prototype from form of the chip is manufactured. Now, why do we need this prototyping step? That is because there are some issues which we cannot take care or which we cannot think of during implementation, like when we think of a very deep submicron level technology, there are electrical effects and all those things which are not possible to model during implementation. So that is why we create a prototype, and then we try to go for manufacturing. But when during these 3 steps, we try to fix all the design bugs that are present in the specification or implementation or prototyping. So these are basically a feedback loop kind of thing. From specification, implementation is done, and if we find that there are some part of specification which is not consistent, like that is some part of specification is conflicting with the other part, then we need to rectify the specification itself. Then in the implementation, we try to find whether the implementation is satisfying the specification or it is correctly implementing the specification or not. Then we come to the prototype and we try to verify the entire specification, what we have intended to do is taken care of by the prototype or not. So due to the other external effects, the intent is not lost, like what we have specified, we are getting that at the prototype level. If we find some bug during prototyping, we go back and again try to rectify the implementation to take care of the effects which are causing the bug. Now, these entire 3 things are the part of design validation. So, and from the prototype to manufacturing, we do testing. Testing is required to make sure that whatever we need, we intend to design is actually designed. So, during the design manufacturing process, no external errors got introduced into the chips. So that is why we do testing. So testing is per chip basis, whereas the verification, this is per IP basis. Like for a particular chip, we do the entire thing once, then we start manufacturing that chip again and again. Now, the implementation part, if we get a more clearer view to that implementation part, it has the following steps. we start with some component specification document, which are basically English document that gives high level description what is expected from that component. Then the designer makes an RTL implementation of that. Now since the modern day chips are significantly large, so one designer is not able to do the entire implementation. So typically what is done, all the entire design is broken into some module, into some modules, and each of the module is implemented by each of one designer or something like that, by a group of designers. So in RTL implementation, suppose for the design we need n modules. Now each of the n module will be written in Verilog or VHDL. So that is what after this step we will have n Verilog descriptions that together will make this design. Now once we have these n individual Verilog descriptions of the modules, we need to integrate those descriptions, like suppose there are 3 Verilog modules here. Now these inputs of one module might be connected to the output of other module, like this. So this interconnection and the entire design is integrated in this phase. So in this case, after this phase we will have the entire design in Verilog or RTL level. So once we have the entire design, we do the verification, that is we have some properties, we extract out some properties from the specifications and try to verify whether these properties are holding on this entire integrated design or not. Now from design integration we use some automatic tool, to generate this netlist automatically. Like if these are typical RTL level descriptions and these are typical and or these kind of gates we will have after this gate level netlist. So after these things we won't be having these module level boundaries. So instead of that we will have an entire big flat module which consists of only gates, and we will have a set of input here and a set of output here. Now after this after creating this gate level netlist, we do the technology mapping. Like suppose we have an AND gate here. Now this AND gate can be implemented using TTL, CMOS or whatever with some present technology. So from here we create these transistor level implementation. So basically all these gates will be some form of transistors here. Now since these two steps, like this synthesis and this technology mapping is done by tools, and tools are not bug free, so there may be bugs in the tool. So we need to ensure that whatever is here will be converted correctly as the netlist, and from the netlist this transistor level is created correctly, and for that reason we do equivalence checking. Like what is equivalence checking? It is basically we create some model of this integrated design and we create some model of this netlist and try to prove that these two are equivalent. The same thing is done here also. So overall the verification part comes into the first part, where the specification, we check the specification is holding on the integrated design. Still this portion it is readable, human readable. So if we find bugs, we then again go back to RTL implementation and try to rectify it, and then this part is done by some tool. Now we do that equivalence checking in order to make sure that whatever we make as integrated design comes exactly as the transistor level schematic. Now as I said, that verification can be done through writing some test cases and properties and checking whether the properties are holding while running that test cases or not. Now it can be done in another way, like it is trying to in this formal verification, what we try to do is we try to verify properties over all possible runs on the system, like exhaustively. If there is any refutation of the property, we will get that if we do the formal verification. So we take the specification and the implementation and give it to a formal checker, and it gives either yes, or if it is not, if the specification is not holding on the implementation, it gives a counter example exactly at which sequence of action leads to the refutation of the property. So briefly, the formal property verification is as follows. The entire design intent, that is the correctness requirements, are expressed in terms of formal properties. I will discuss what is meant by formal properties. Then we check formally whether the implementation satisfies all these properties or not. If the implementation satisfies all the properties, the checker reports success, otherwise it gives a counter example, and this entire method is known as model checking. Now for hardware, verification, we have Verilog codes here. Now from this Verilog code, we extract out some Kripke structure, and all these properties are expressed using temporal logic. Now these two are the input of model checker, and model checker verifies whether these temporal logic properties is holding over the Kripke structure or not, and depending on it gives yes or gives no. Now let us take some example of the specifications, how the correctness requirements can be specified. So it can be a Boolean function, like for adder, multiplier, we can give the exact Boolean formula what is expected from the design. It can be some higher level model, as I said in that vending machine. Here from this physical machine we create some higher level model, and the controller of this machine will have some Verilog description, and we can check whether those that Verilog description is equivalent with this model or not. So, and the third way is to specify specify a set of temporal properties and checking whether this set of properties is satisfied by the implementation or not. Now for the first two, we what we do is basically we convert those two things, like either this is a higher level of design and the implementation at a common platform. We bring those two at a common platform and do the equivalence checking between them. So typically BDD, BMD, SAT-based formulas, those are used for this equivalence checking, but we will not cover this in this presentation. The third one, we for the third one, like for verifying temporal properties over some implementation, we do formal property verification. Now to understand what is meant by temporal properties, first let us see what is meant by propositions. This propositional logic. So propositions are basically facts, facts about environment, facts about anything you can have. So these propositions can have two values, true or false. So the sun rises in the east, it's a fact. It is raining, it's a fact. So all these are propositions. So but for all number x, there is some successor of that number. These kind of things are not propositions, because here that statement depends on the interpretation whether it is true or false. It is not stating a simple fact, it is allowing variables. So in propositional logic we don't allow variables over facts, like all men are mortal. These kind of facts we don't intend to express in using propositions, only straightforward facts without variable using constants only. So like let's take a very simple example. It is raining if it rains the streets will be wet. Now common sense says that from these two facts we can deduce that the streets will be wet. Since it is raining and the second thing says if it rains the streets will be wet, so we deduce that the streets will be wet. So since we can do it naturally, that is why this kind of deduction is called natural deduction. So if you remember the the theorems of geometry, those are basically natural deduction. You have some set of facts, you have some rules, if this happens then this happens, this kind of things, and you deduce something out of that using those facts and rules. You apply the rules whenever you need them in order to deduce the result. So here is an example of in the slide here is an example of a bit more complicated propositional expression, like if it is raining and Jane doesn't have her umbrella with her, then she will get wet. Jane is not wet, it is raining, therefore Jane has her umbrella with her. So the common structure is if P and not Q then R, and the fact and not R and not P, this entire thing, from this entire we can deduce Q. So this is what abstract form, what is propositional logic. Now okay, I will not go into the details of syntax and semantics. So what we basically do, we try to extract out the entire structure from this. So if we encode this thing using Boolean formulas or Boolean connectives, so it will be something like this: P and not Q implies R, and not R and not P, this entire thing implies Q. So this Q, we can deduce this Q from this if this implication is valid. So the, what is meant by valid is for all values of for all possible combination of values of these P and Q, this entire expression will always evaluate true. So you can try out and see that this will evaluate to true if you, I mean, if you use the normal conversion of the propositional connectives. Now what exactly do we specify using propositional logic? Here these kind of Boolean functionalities are expressed using propositional logic. Like here for a full adder which has two single bit input A1 and A2, we can say that Cout implies and implied by A1 and A2, that is, this is equivalent to symbol. So that's how we can specify properties over propositional logic. Now where does the temporal part comes into picture? Whenever we try to model any system of real life, it involves the notion of time. From time t1, say at time t1 it is in state some s1, then at the next time cycle t2 it goes into some other state, it makes some state transition. So at each of the states some propositions are true, some proposition holds at each of the states. Now if we want to reason about the propositions which are or properties which are spanning over the time cycle, we need the notion of temporal logic. Okay, let us take an example. So this is a round robin arbiter. It has two inputs R1 and R2 and two output G1 and G2. Now since it is round robin, whenever R1 will request, within the next two cycle it will get its grant. So round robin means for it will allocate the grant for a particular time interval to each of the requests. So if R1 makes a request and R2 receives a grant, it will be given the grant for one cycle, then R1 will receive his grant. So the property spans over time cycle, say 2 time cycles. If the request bit R1 is true in a cycle, then the grant bit G1 has to be true within next 2 cycles. So these are kind of notion of temporal properties. Now we can use linear time temporal logic or computation tree logic CTL, that is branching time. I will describe what is meant by linear time and branching time. So these are the two major classes of temporal logics. But one thing we need to remember, that whenever commonly temporal logic is specified, that is propositional temporal logic. That means we reason about propositions in each state and over the time. We do not have any notion of like this for all x, uh, x implies y, something like this. For all there exists quantification of over I mean this kind of variable. We don't have the notion of variable in propositional temporal logic. All these have to be some constant, this x, this y. Now again I try to describe what is meant by the temporal. So this is again this is the round robin. Now initially R1 is low, R2 is low, G1 is low and G2 is low at time 0, and at the next time cycle request 1 comes, request 2 comes, and okay, fine. So these are I mean if we enumerate this entire thing over the time, like at time cycle we will at a particular time t we will have some value for R1, some value for R2, some value for G1, some value for G2. Again in the next time frame we will have another set of values for R1, R2, G1, G2. This one is for the time instance it is talking. Now here like we can write the formula mathematically, like for all t, for all time instance t, R1 at time t implies G1 at time t plus 1 or G1 at time t plus 2. So this for all t part, this is the only variable that is used in temporal logic. Since this t is the only one, it is taken as implicit time variable. So we don't write for all t always. We simply write always R1 implies next G1 or next G1. Here next means the value at next cycle. So okay, these are the basic set of temporal operators we have. One is next step, that is next is f is true in the next cycle. The second one is gf. G stands for global, like for all values of for all time t, f will hold on every state. F is even f expresses eventuality, that is f will be true in some time cycle in future, and this one is f until g, that is this is basically we will have a sequence of f, then we will have g. So before the first occurrence of g we will have a continuous sequence of f. Okay, let us describe these things in a more detail. So suppose this is the initial state, xp means in the very next state p has to hold. So basically these temporal logic properties are interpreted over a sequence of states. That sequence of states basically are the run which we are the runs on which we try to verify the property. So in on this run the xp is holding, this is the initial state, this is where p is true. So xp holds in the next state. Now gp means in this run or in this path at all states p will hold, then only gp is true on this sequence of states. Or alternatively we can think of not p doesn't hold in future. That means if p holds always, not p never occurs in future. So we will see that the dual of this g is f. So this f P holds eventually in future. That means it may be here, it may be here. We don't specify any time bound when it will hold, but somewhere down the line it will hold. So again, it alternatively means not P doesn't hold always. P until Q is something like this. Uh, we have a continuous sequence of P and then we have Q. But what is ensured by this property is Q has to hold eventually. It cannot happen that P holds infinitely and Q never happens. Then this property will be false. In order to hold this property, Q has to hold eventually, and when Q holds till the previous state, P has to hold continuously. Now this is the duality between G and F. GP means P holds always, that means not P does not hold eventually, not P holds eventually, that is not future, and can do the reasoning. Now we can have nesting of these temporal properties, as we have seen that GP means from GP means P holds globally. Now what does future GP means? Future means from this state we have a future state, along this path there exists a future state from where the P holds globally. So this is like this. Now there is another property, that is global future P. What does this mean? Future P means eventually P has to hold. This global ensures along this path from all states this future P has to hold. So that means whatever state you take from this sequence of states, from that you will have a future state where P is holding. Now these are some examples where future P. So we have, like for this property future P along this path from this, but here this P is holding, so future P hold along this path, this path, this path. One thing we need to remember when we write only future P, only global P, these are linear time properties. Since we are interpreting the properties over a single path, and what is meant by from a particular state future P holds is from that state in all possible paths this future P holds. So this notion shows along this path how future GP, or say this one, along this path how P until Q can hold. Now when we say that starting from S0 this property holds, that means from S0 we have here 1, 2, 3, 4 paths. Although these paths will go towards infinity, but there are 4 paths, and along all paths this future P is holding. Then only we can say this future P holds in this holds for S0. Similarly Q until P, here also you can check that Q P. So along this path Q until P is holding, along this path also Q until P is holding, Q P. So now future GP, the same thing, from this state along all paths there exists some state from which P will hold forever. Since here once P holds and it loops into this state again and again, so from the here you will have GP true, again from here you will have GP true. So from all those states along all paths you will have GP true. Now let us discuss what is meant by safety and liveness properties. Basically safety properties are something which has to be true globally. That means if we watch for the if we watch the state machine for finite amount of time, we can see the violations. So it is like typically the structure of safety property starts with some global some formula. So say X A implies X B, something like this. So these are basically safety properties. So globally for all states, whenever A happens in the next cycle B happens. So now on the other hand there is another class of properties that are liveness properties. Those are like we try to express that something good will eventually happen, like whenever somebody will make a request, eventually he will get the grant. So these kind of properties we write through using this kind of properties are called liveness properties. The same thing, starvation from freedom and all those things are liveness properties. Now we discuss what is called path quantifiers. As we have seen that in LTL, it is necessary to hold a, I mean for a implementation or for a state transition system to satisfy a formula, it is necessary to satisfy along all paths. In the same way, we can reason about for all paths and there exists a path. This kind of distinction we can do. In LTL, we cannot distinguish between these two options. So from that point of view, another kind of logic that is called branching time logic is developed, and to express the quantification over paths. So it is like there exists a path. Now here we have, if the property holds along this path, then we can say that it is true over this system, and for all path means it has to hold on all path. Now let us distinguish between these two things. No, in LTL implicit assumption is the property has to hold on all paths, as I shown here. Like for future p, if it has to be true, then it has to be true in over all paths. So LTL, that is the notion of linear time. From its state, you can think of it can hold some path, hold on some path, cannot hold on some path, something like that. But for that reason, you need the notion of state. LTL is path formula, so it holds on path. Now, from a state, you can reason about there exists some path or for all paths. So that is why we need these state formulas. That is where CTL comes into picture. But intuitively, it is difficult to write formulas using CTL. That is why people prefer LTL. Now, what is meant by this formula is like along all paths from the state S, P is true forever. Okay, let us see some example that will make it easy to understand. Now, typically these are the implementation kind of thing. Like at this state AB, proposition AB is true, at this state C is true, at this state BC is true. Now we can unfold the state machine like this. From AB it can come BC and it can go to C. From BC again it can come to AB and it can go to C. From C it can go to C only. So this kind of, so from the starting state we can have this path, we can have this path, this path. So if we want to reason over individual paths, like if some property holds on some path, then we need the CTL to express the properties. Let us see what is basically the syntax of CTL, then we will have some example how properties are written. Now in CTL, every temporal operator is preceded by A or E. That means from each of the state along all paths or along some path. That is the distinction between A and E. And in CTL we have only state formulas, that is formulas which will true on a state, on a particular state. So and from that state we try to quantify the paths. Let us have some example. Here we have the formula AXP. Now from the starting state across all paths next P will hold. So now this formula has an equivalent expression in LTL also. XP from this state will have the same interpretation, but there are formulas which we cannot convert, like there are formulas in LTL which we cannot write equivalent in CTL and the vice versa. I will discuss that. So these are the notion of AX. Now universal, well, A means always starting from this state across all paths. Now GP globally P, so across all paths globally P. Along all paths future P. So in this state, in this path and this path, here P holds. In this path this holds. So That's how AFP holds. These also along all paths P until Q holds, like P then Q, P P then Q Q. So this is holding. Now let us see some example of existential path quantifier. That is, starting from this state, along there exists a path where the next state there exists a path where in the next state P will hold. That is the notion of EXP. So either of these, if P may hold here, P may hold here, but wherever it holds, it will satisfy EXP. EGP means there exists a path where globally P will hold. EFP means there exists a path in which P holds eventually. That means it may hold here, it may hold here, but in some path it will hold. Similarly, this P until Q also, there exists at least one path where P until Q will hold. So P until Q holds in this path. Now let us consider some bit more complicated properties of CTL. Yeah. BTL? No. That is LTL. No. Compute branching time logic. I mean, we don't use the acronym BTL for that. Computation tree logic is the full form of CTL, and we enumerate all the computation tree and try to interpret the properties over the tree. That's why it is computation tree logic. BTL is not a very popular acronym. So the other temporal logic is LTL. So this is always from the next state, always global P will hold. So these are pretty much straightforward. Like we will have this kind of thing. From the next state onwards, across all paths, this GP will hold. Now EXEFQ, that is something starting from this state, there from this state along some path we will have some next state from where future Q will hold. Now consider the last one, always global exist future R. But basically this means across all paths globally this will hold. That means from all states we will eventually reach R. That is something the notion of Liveness talks about. Like eventually something will happen. Here we encode that by R. So this expresses some Liveness properties. Now here is the example where these two logic differs, like future global P and always future always global P. Now on this implementation, we can see that this future global P, that is true in this, but always future always global P is not true. Let us see why it is not true. What future global P means, that starting from these states across all paths, in future globally P will hold. It does not talk about the formula has to hold on a particular state. It talks about the formula has to hold on all paths. So whatever path you can take, you can see globally P will be true. Red marked states are P level states. So in this path, wherever you go, globally P will eventually hold. Now always future always global P talks something different. What it tells is from this state, this is a state property. So truth of this property is associated with this state. So from this state across all paths, we will have some state where this always global P will be true. Can you see where it is refuting? Think of this path. What is happening in this path? In this path, nowhere in we don't have a state from where this always global P is true, because whatever states you take from this path will refute holding this property. So that is the difference. That is the difference between the expressive power of LTL and CTL. So there are more examples, but I will not go into the details. Now here comes the second part of the verification. So till now what we have seen is how to specify properties using temporal logic. Now we need to check whether the property is holding or not on some model. Typically that model is a Kripke structure. Okay, so now consider this state machine which has two states S bar and S, that is S equals to 0 here, S equals to 1 here. I use that notation. Now at this state the I, as long as the I is false, it comes back, loops back to this S bar state, and when I is true goes to the next state and stays there as long as I is true there, and if the I is false it comes back to S. Now this is a typical example of finite state machines. So from current state, depending on the input, it makes the transition. Now to verify some property over this kind of implementation, we convert this into Kripke structure. So what is the corresponding Kripke structure here? Let us consider this is the starting state here. In Kripke structure, we the typical, this is the FSM. So here we have inputs. In Kripke structure we don't have inputs. The notion of input is taken care of by the state machine itself. Let us see how does it do that. Now at state S bar, the input may be I bar, at a state bar the input may be I, and we assume that initially the input is I bar. So this is the initial state. Now if this is S bar and I bar, so it will go to this state or this state. Now from S bar, I bar is true, it ensures that it will loop back to S bar, but in the next state we don't know whether I will be true or I bar will be true. Now to take care of the input, we add non-determinism between these two. So from this state it can go either this, loop back to this one, can go here. Similarly we have Si here, Si bar here. Now from here Si, since if it receives input I, it has to go to S. Now S is true here, S is true here, so but we don't know which one of the input will be true here. Again in the same way, from Si it will loop back here, and Si bar it will loop back here. So this is the corresponding Kripke structure to this FSM. Now think of this priority arbiter. Suppose we have a property, linear temporal logic property, like globally G1 or G2 is true. So first we make an transition relation from this state machine, from this implementation, that is G1 dash is implies and implied by R1, and G2 dash is implied if R is low and R2 is high and not G1, then G2 will, in the next state G2 will be high. So this dash denotes the next state, the value at the next states. Now these are the starting state. So we can have a table like this. This is the present state, this is the input, this is the next state. So the entire table we can enumerate. Then this is the Kripke structure as we have shown in the paper. So here this will be the start state 0 0 0 1. So this is the start state. So from where it can make transition to here, any of these 4 states. So what we need to see is, in this uh, entire state machine, we don't have any input. We have taken care of the input as a part of state. That's how this non-determinism is introduced, but uh, we don't have any external input, and over these kind of state machines or Kripke structures, we have we verify the properties. So okay, so this is the formal definition of Kripke structure. So what we have, atomic proposition, as I said that whenever we try to write properties, we write properties with respect to some propositions. Now some, at some state some propositions will be true, some subset of propositions will be true. So this, if AP is the total set of atomic propositions, atomic propositions means it can have value either true or false. So at each of the state it will have a subset of the AP which is which will hold on that state, and this R is basically subset of S cross S. That means from this state it will have multiple set of states from to where it can make the transition. Now a path in this Kripke structure is determined by is represent like this: S0, S1, S2, like from the starting state. Let us start with this one. S bar I, so this is basically path in that Kripke structure. If we allow the system to run, the paths through which it can traverse, the paths we can consider. So this is basically S0, S1, S2, it goes on. Now this is an example of Kripke structure. Here we have AB as propositions at state S1, or sorry, this Q1 we have A, this Q3 we have B, and Q2 we have AB. Now these are the sequence of states which is represented as a path. So from Q1 it goes to Q3, then again comes back Q1, Q3, Q1, like this, and then eventually goes to Q2. So that is one path, and along each path these are the traces. That means which are the which propositions are holding across this path. Like here Q1 A is holding, Q3 B is holding. Now whenever we talk about verifying properties, we try to verify properties on these kind of traces. Like here we can see next B is true, like from A to B, from A to B, from A to B. So we can say the next B property is true in this particular Kripke structure. So I don't go into the details of the verification process because that is beyond the scope of this class. These are the references. Any questions? If you don't have any questions, then thank you.